Have you ever stopped to wonder how we actually know what stuff is made of? I mean, down at the atomic level, in a world that's way, way too small for any normal microscope to see. Well, today, we're going to peek inside that secret world. We're going to explore an incredible technique called X-ray diffraction.
So here's the game plan. First, we'll tackle the huge challenge of trying to see something that's literally invisible. Then, we'll get into what X-ray diffraction actually is and uncover the secret sauce behind it, something called Bragg's Law. After that, we'll learn how to read a material's unique fingerprint, and finally, see how this amazing tool is being used out in the real world.
All right, let's start with the big problem. Our entire world is built out of atoms, right? But how in the world do you study something that you can't possibly ever see?
I mean, this is the question that really had scientists scratching their heads for decades. If you want to understand why steel is strong or why a diamond is so hard, you have to know how its atoms are arranged. But how do you draw a map of a city when you can't even get a single picture of a single building?
You see, the magic of a crystal isn't just what it looks like on the outside. It comes from this hidden, perfectly repeating pattern of atoms, all locked together deep inside. That internal order, that's the secret we need to unlock. And the key that finally let us unlock that secret? It's a really ingenious technique called X-ray diffraction, or XRD for short. This is the tool that gave us a window into the atomic world. So, what is it really? Well, simply put, XRD is a way for us to figure out the atomic structure of a crystal without destroying it. It's kind of like being able to get a perfect blueprint of a building's entire internal framework just by shining a special kind of light at it. And here's the absolute core of it all. When you shoot X-rays at a crystal, the atoms inside scatter those X-rays in a very, very specific way. The pattern that comes out is completely unique. It's a literal atomic fingerprint. No two materials with an ordered, crystalline structure will ever have the same one. Ever.
Okay, this all sounds pretty cool, right? But how does it actually work? How do you go from just shooting X-rays at something to getting this detailed fingerprint? The answer is in a beautifully simple piece of physics called Bragg's Law. Let's break it down. So the first concept you gotta get is something called constructive interference. Just imagine two waves meeting up. If their peaks and troughs line up perfectly, they add together and create a much bigger, stronger wave. That's the signal our machine can actually detect. But on the flip side, if those waves are out of sync, a peak meets a trough, they completely cancel each other out. That's destructive interference, and it gives us, well, nothing, no signal. So for XRD to work, we are only interested in those very specific, perfect moments where the waves add up and amplify each other. So how does this wave stuff apply to a crystal? Well, here's a great way to picture it. Think of a crystal structure as a perfectly ordered stack of really tiny, semi-transparent mirrors, where each mirror is a whole layer of atoms. Okay, so when X-rays hit this stack of mirrors, some will bounce off the top layer, but some will travel a little deeper and bounce off the second layer or the third. Now, for all those bouncing waves to line up perfectly, to be constructive, the extra distance that deeper wave travels has to be just right. It has to be a perfect whole number of wavelengths. Not 1.5, not 2.7, exactly 1 or 2 or 3. And this brings us to the final piece of the puzzle, Bragg's Law. It's this really elegant equation that just ties everything together. It shows that you'll only get one of those strong signals at very specific angles, and those angles correspond perfectly to the spacing between the atomic layers. So, by measuring the angles where we see a big peak, we can calculate the exact distance between the atoms. It's brilliant. All right, so we've fired our X-rays. Bragg's Law has done its thing, and we have a signal. What do we actually get? Well, we get a graph, that unique pattern we've been talking about. Now let's figure out how to read it. This is it. This is what a scientist sees, an XRD pattern. Now, at first glance, it just looks like a bunch of spikes on a graph. But every single feature of this graph, where the peaks are, how sharp they are, how wide they are, is a vital clue to what's going on in that material's inner world. So you have to know what the clues mean. The position of a peak along the bottom axis, that tells us the spacing between the layers of atoms. How sharp and pointy a peak is, that tells us how perfectly ordered the crystal is. And even the width of the peak can tell us the average size of the tiny little crystal grains inside the material. Let's just focus on that peak sharpness for a second. See on the left those really sharp, well-defined peaks? That's the signature of a highly ordered, very crystalline material. But look at the right. When the peaks are all broad and washed out like that, it's telling us the material is disordered or amorphous. Its atoms are all jumbled up. It's a direct visual readout of internal perfection. Okay, we've gone through the theory, we've looked at the data, but why does any of this actually matter outside of a lab? Let's take a look at how XRD really impacts our lives. It's honestly incredible how much information you can get from just this one technique. Scientists can figure out exactly what different materials are in a sample, how its atomic framework is built, and how ordered it is. They can even tell if the structure is under stress, measure tiny grain sizes, and hunt for impurities. It's a shocking amount of info from a single scan. So let's just recap that whole workflow one more time. First, you hit the sample with X-rays. Second, the atoms scatter those rays. Third, those scattered rays interfere with each other. Fourth, that interference creates a unique diffraction pattern. And finally, we record the peaks from that pattern and analyze it to figure out the structure. It's a really clear, powerful process. And because it's so powerful, its reach is just vast. Engineers use it to design stronger alloys for airplanes. Doctors use it to check bone health and to develop new drugs. It's absolutely essential for making the microchips in your phone and for analyzing minerals in soil. It is, without a doubt, a cornerstone of modern science. And here's a perfect example. XRD can tell us how atoms are stacked. So in what's called a face-centered cubic arrangement, which you find in aluminum or copper, the material tends to be soft and easy to bend. But in a body-centered cubic arrangement, like an iron, the material is way stronger and more brittle. This shows you right there how the atomic arrangement directly controls the properties we see and feel. And that right there is really the main takeaway. Everything about a material, its strength, its color, whether it conducts electricity, it all comes down to its atomic structure. And XRD is our most powerful tool for actually seeing that structure. From developing brand new medicines to creating unimaginable materials for space travel, the ability to see the atomic world has just opened up endless possibilities. And it leaves us with one really exciting question. With this incredible new way of seeing, what are we going to discover next?